Okay, so let's continue the previous topic uh, about gain function of the wave equation. So last time we started so basically we are solving this equation in different dimensions. So it has some right hand side. And to solve this equation with arbitrary right-hand side, we need to solve the corresponding equation for the gain function, which has this form. So and we are doing this using the Fourier transform, and the corresponding computation looks like this, and that gain function in the coordinate space is the inverse Fourier transform of the gain function in momentum space. So this is one of several gain functions, and so-called retarded gain function. And, last time we computed the first integral in the omega plane, and now we are left with a single integral, well, with this multiple integral in the momentum space. So as a result of this computation, for the first time for a transform, and gave us the gain function of some one-dimensional equation with the Laplacian replaced by k squared, and it has the following form. It is sine of absolute value of k times t over absolute value of k. It's a result of omega computation times I k r and that's it. So, do you have any questions about this computation? So, about this formula. So this was obtained by a residue computation in this integral with contour. Also, a heaviside theta function of t that vanishes when t is negative. This was obtained by this residue computation. And the contour was this, and it was closed below. For positive time, and for negative time it can be closed above, and it gives 0. Well, it's the same. So ah, two terms in the sign are two contributions from these two poles, and k in denominator is a contribution from this denominator. So we have this integral, which is universal for all dimensions. But now, differently from all other equations, well, actually not all others, but for many other equations, dimensionality of the space-time matters, and this integral should be computed differently for different ends, and answers are also different. So uh, we need to do several computations, and let us start from n equals to 1. So in the first case, n equals to 1. So this is the case where we already know the result, because we were able to solve this equation without all these Fourier transforms, gain functions, and so on. We could just integrate it twice and get some formula. So in this case, we have we said theta times integral from minus infinity to plus infinity, decay over 2 pi, sine of absolute value of k t over absolute value of k, e to ikx. Simply x, because there are no other components. It's one-dimensional. So here we can notice that this function is asymmetric with respect to k to minus k. So we can simply remove the absolute value of k. So so it looks a little bit simpler. And also another thing which we can do is we can move this contour slightly above the real line, or maybe below. I don't know what is better. Maybe let's move it below. It does not matter, because zero of sine at k equals to 0 cancels with 0 of denominator. So this expression is non-singular at 0. But if you want to split this integral into two parts, it's better to have two integrals which are well defined. So in order to do this, we can modify this contour a little bit from the very beginning. So and we can also write the sign as a difference of two exponentials. So we can write it as this. Say theta h t. This is 0. Contour is shifted slightly below. Decay over 4 pi I. And here we have two exponentials. 2 pi I k e to I k t plus x minus e to I k x minus t. right? Simply I simply combine this argument with two exponentials that come from sine. So, so uh, uh, let us write this. So now we can split these two integrals because both of them are well defined on this contour. So uh, k over k e to I k x plus t. Mm, maybe x plus t. And this integral over the same contour. Mm. So now the question to you. This x plus t and x minus t can be positive or negative. Uh, Maybe let us compute one simple integral here and use it later. So we want to compute the integral dk over k e to I mm, alpha k over this contour. What does it equal to if alpha is real, or if alpha is positive? Uh, how can we close on this contour? Yes, because in this case k goes to infinity multiplied by I goes to minus infinity, and this goes to 0. So we have this picture. And what does it equal to? Mm-hmm. And what is this residue? Yes, but multiplied by 2 pi I. Because, mhm. In this case, it goes counterclockwise, so everything is fine. If alpha is less than 0, then this contour can be closed in the opposite direction, and it gives 0. So overall, it is 2 pi I times heaviside theta of alpha. So let us use this knowledge in this case. We have overall heaviside theta of t 1 over 4 pi I times 2 pi I that comes from here, and then heaviside theta of uh, x plus t minus heaviside theta of x minus t. So it is 1/2 sine theta of t sine theta of x plus t minus sine theta of x minus t. So, and if you draw this in the x t plane, then it looks like this. So it's 0 for negative t, uh, and it is 0 for very negative x and very positive x, but it is non-zero in the interval from minus t to t. So there is this cone. X equals t, x equals minus t. And in this cone, this gain function equals to 1/2. And in this region, it's 0. So if you kick your string at a point at a given point and a given time, with this delta function like force in the right hand side, it produces a wave of this shape. It has two wave fronts on the left and on the right, and the value of deviation of your string in between is constant. It's 1/2. So it's not very nice function because it discontinues here and there. So it evolves like this. So, but in all real problems, it will be integrated with some smooth function appearing on the right hand side. Maybe. Oh. But it's essentially a gain function that we already know. Is it fine? Oh. So if you want to write a solution with arbitrary right hand side, minus uxx equals to f of equals to f, and then u of t and x equals to 1/2 integral from minus infinity to t, integral from x minus t minus t prime to x plus t minus t prime. Yeah, it's fine. F of t prime x prime, t prime dx prime. This is what this gain function gives us. So when we sit at the given point, we need to collect all contributions of this plane waves that can come from points in this cone, because all other waves will simply be unable to reach this point. And mm, 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 we need simply to compute this average of force on the right hand side. But this is what we already know. And let's go to next case about which we know more or less nothing except for our everyday experience, because we see how sound and light and all other waves behave. So let's first go to the three-dimensional case. And I'll show you a bit later that it is simpler than the two-dimensional wave equation. So in this case, this ungained function is given by this expression. So we now have three-dimensional integral. So we need to compute this integral, and the main idea to do this is to switch to spherical coordinates. This integral should be computed for some specified value of x, and we can choose direction of x as the axis, and introduce spherical coordinates using using this. So we have a picture like this. X, Y, Z. Let us say that K is pointed towards this direction. Oh, no, not K, X. And let us say that the absolute value of X is, well, let's simply say that it is it equals to absolute value of X without introducing any other. Maybe. Or maybe let us say that a absolute value of X is R. I forgot that we have three coordinates x, y, z. So x itself equals to x, y, and z. Wait, maybe. Let me maybe change the notation, because it is confusing if we have x vector and x in the first coordinate of this vector. Let us say that it is a radius vector, and this is denoted by r. And then this notation is also a bit more consistent. So there's a coordinate system, and we introduce spherical coordinates like this. We have vector k, and one angle is this is theta. Maybe let me use a different color to draw this vector. So we have vector k living in this coordinate system, and one angle is measured like this as an angle to the axis, and then we also have a projection of this vector to the xy plane. And another angle is called phi. So if you look at this picture, uh, how would you write transition between kx, ky, and kz to spherical coordinates? So we have kx, ky, and kz, and they should be um, related to absolute value of k, theta, and phi. So, okay, can you tell me what the value of kz is? Mm-hmm. Thanks. And two other. Mm-hmm. Mm-hmm. Thanks. Yes, that's one part of transition. And what is the Jacobian of transition between these two coordinates? So we know that if we need to write one integral in terms of another one, then we have dk x. Do you already know about differential forms? So if I write like this, will it be fine? Oh. Mm. So is it fine to write like this? So, so we can also say that it's a volume element written in different coordinates. And of course, it can be computed as determinant by definition, but we can also draw a picture that tells us how to express the volume element in spherical coordinates. Uh, So this picture looks like this. We have uh, we have a sphere, and we have uh, a belt that corresponds to fixed value of theta. But this belt has a thickness delta theta. So 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 its thickness is delta theta. Mm, in this direction, and in the other direction, maybe this colors help. We have so in the other direction it has a thickness delta r. So uh, here we have a segment. Uh, so maybe let us look at this in a different projection. So if you look at the projection to xy plane, or sorry, xz plane, we have something. We have a sector delta theta here, and delta r here, and delta sorry delta k. So then this is made three-dimensional. So it's a section of this belt. Mm. And if you want to compute, and we also need to take as part of with delta phi. So to compute the volume of it, of this segment of size delta theta, delta phi, delta r, delta k, we need to multiply delta phi by the area of this section. Delta phi times times sorry, delta phi times not delta phi times not just delta phi but delta phi times the radius of this circle, and this radius is equal to what? Okay. It is r sine of theta, k sine of theta, absolute value of k sine of theta, because it is this distance. Area of this piece. And what does this equal to? So delta k. And this equals to absolute value of k, of course. Could you say it again? No, because this is measured in inverse meters. Well, in inverse distance, well, in distance units in the k space, and this is dimensionless. Area should have a definite dimension. Well, it should have dimension 2. But if I ask a simple question, if you have a ring of a radius uh, absolute value of k and with delta k, what will be its area? Uh, ah, mhm. uh, yes, and so yes, so here I want to compute the full the area of full news of segments and delta k. So this equals to 2 pi k delta k, right? Uh, so this one should equal to not 2 pi k delta k, but delta theta k delta k, right? So so if you combine all this together, we get uh, delta k. We get so total of k squared sine theta delta k delta theta times delta phi. So And it has dimension 3 as it should be, because there's k squared times dk, and some dimensionless factors. Right. Okay, we could actually find this determinant, this Jacobian connecting different coordinates without computing it. So we can simply write that it equals to absolute value of k squared sine theta. Yeah, and if we were working just with polar coordinates with radius and angle, then this Jacobian would be equal to this expression. So, okay, we have this transition between different coordinates, and let us apply it to our integral. So. Maybe. So, by the way, the question about this change of coordinates. What are the domains? Maybe let's ask it when we write the integral. What should we write for the domain multiplication in absolute value of k? Yes, it's from 0 to infinity. What to write for phi? Um, no, actually 2 pi, because this angle can be arbitrary. There is no relation between this point and this one. They, they have different phi's. And what for the theta integral? Yes. Uh, so now everything is divided by 2 pi third. And we have this expression that is the same, sine kt over k, and the exponential. And what should we write in the exponential? If we choose spherical coordinates like this, choosing z axis parallel to r.
R plus times values of k times cos of theta.
R, K. Thanks. Yes, and we also have integration measure, which I'll probably, well, I can write it here. Sine theta k squared. Uh, so now notice that this k can be partially cancelled. So first thing to notice. And one more thing to notice is that we can combine d theta and sine of theta into d of minus cosine theta. And this minus cosine of theta changes from oh, how should we call them? Let me write it as minus d cosine theta. And cosine theta, this cosine theta changes from 1 to minus 1. Then we will flip on this domain of integration. Another thing to notice that phi integral is equal to 2 pi. It doesn't, this expression under the integral does not depend on phi. So this is simply 2 pi. So what we have integral from 0 to infinity k dk over 2 pi squared. We have integral from minus 1 to 1 d cosine theta. And we have sine kt e to I kr cosine theta. So can we now compute the integral in cosine of theta? So it appears only in the exponential. Hmm? But it does not depend on theta. Hmm? What do you mean? So it's just a single variable, cosine. This one? Yes, of course. Yes, we don't care about this. But how do you integrate the remaining part? So, of course, there is sine kt over 2 pi squared. But what to do with the remaining expression? Of course, we can move it here.
divided by IKR.
Mm-hmm. From cosine theta equals to -1 to cosine theta equals to +1. Right? So this k here cancels on this one, and this expression combines to 2 times sine of IKR, right? We have integral from 0 to infinity, decay sine of kt over pi squared to IKR minus e to minus IKR over IR. And maybe I will not even write it as a sign. It's better to work with exponentials. So, we have this. Now we can also notice that this expression is k to minus k symmetric. So, are there any questions on this? So, as long as this expression is k to minus k symmetric, I can extend this integral to integral from minus infinity to plus infinity. So, can write it as 1/2 times integral from minus to plus infinity. Decay over 2 pi squared. And let us write this signs as exponential explicitly. E to I k t minus e to minus I k t over 2I e to I k r minus e to minus I k r over I r. Okay, and now let's combine all these factors. So it is it's minus 1 over 16 pi squared. Integral from minus infinity to plus infinity and decay. And if you open all these brackets, we will have 4 terms. E to I k t plus r plus e to minus I k t plus r minus e to I k t minus r minus e to I k r minus t. Is it fine? So simply open all brackets. And I also missed the factor of r. So there is r in the denominator. So can you now compute this integral? Yes. Can you compute each of these integrals? So -1 over.
We computed before.
Hmm? Uh,
Computed before.
well,
The integral minus the plus infinity of e to the I alpha.
but there is a difference. We had the k in the denominator in this case, but in this case it disappeared. And this is actually simpler. So, hmm? But first question is that this integral is not absolutely convergent, and it's not convergent actually. So it's some different object. So what is this object? Yes, yes. Hmm. Yes, actually with a factor of 2 pi. So let us write this. So we have -1 over 16 p pi squared r. We have overall factor 2 pi for all these delta functions. And let's write all of them. We have delta of t plus r. We have delta of minus t minus r. We have delta of t minus r. We have delta of r minus t. There was also heaviside theta prefactor in front of all this, which I missed at some point. Sorry. So also here, so it's non-zero only for positive times. Here. And here. Uh, now let's look at these delta functions. T is positive because otherwise this heaviside theta vanishes. R is also positive because it is a distance to the origin. So these delta functions can never be zero. Yes. So this is always positive. This is always negative. So overall, we can say that these two functions, these two delta functions, always vanish. And these two delta functions are the same because the delta function is in a sense symmetric because it computes the value at zero of function phi of x. If you change it to function phi of minus x, its value at zero will be the same. So we can say that these two delta functions are equal. On combining all this, we get the side theta of t over 4 pi r delta of t minus r. So maybe we can write r as the absolute value of a vector in this time, like this. So this is our gain function. And this is also called, if you draw a picture, then mm, draw a picture uh, in the ATR plane. Mm, hmm? No, because these two delta functions are equal. They produce an extra factor of 2, and we already had 2 pi, so it cancels. So this gain function is non-zero only here. Or if we draw it, if we draw an evolution of this solution, then a picture will look like this. We have our three-dimensional space. We have a we have a point source at 0, and it emits a spherical wave, which uh, 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 propagates with the speed of light or of sound. Mm. And we have non-zero value of solution only at this sphere of radius t. And this is also called the retarded potential. Or maybe let me first write some different formula and then explain its name. So, so well, maybe I can erase this. So if we now want to write a solution of our equation, TR, it is given by the integral with a gain function, d prime dr prime. Gain function of t minus t prime, r minus r prime. F of t prime r prime. And if you now substitute this answer on the gain function, then the Heaviside theta function cuts the time integral from a minus infinity to t prime. From minus infinity to t prime, dt prime. And let us keep the delta function for a while. It will be delta minus t prime minus absolute value of r minus r prime divided by r minus r prime. Also integral in dr prime f of t prime r prime. But in this particular case, we can compute the integral in t prime, right? It simply lands us on t prime that equals t minus r prime. So we can write this as the integral in dr prime pi f of t minus r prime over pi r minus r prime. So d3r, here also d3. Well, this dimension is important. This formula is called the retarded potential. Which means that to compute the potential created at point T and R, we need to look at the value of the right-hand side of our equation at point R prime at the time given by the time of our interest minus the time that the wave needs to travel from that point to a point where we compute our solution. So this is this time. Everything is propagating with the speed of light or of sound, which is put to 1 in all our problems. So if something happens at point r prime, at time t prime, so if something happens at this point, we need to compute the time it takes for this event to make some influence on our point T and R. So, for example, if you put some source that emits waves at the origin. Uh, and then this waves will need some time to travel to a point of our interest. And this is precisely what is expressed by this term. So let us consider this example. Let us say that f of t and r is just a point source at the origin. Delta function times a function of t. And let's substitute it into this formula. So delta prime. So what do I get if you compute this integral? Sorry, no, it's fine. Yes. Mm. So it's delta of r prime, because I'm substituting this right hand side, which is a point source at 0, with strengths depending on time.
We just substitute r prime equals to r.
Why r? It's delta function of r prime. In a sense, this delta function vanishes so this delta function computes everything at 0.
So we just get the argument with the r prime equals to 0.
Yes. Mm-hmm. Yes. Thanks. So. Mm. It's actually very similar to what we had in the one-dimensional case where we studied uh, the solution with non-trivial boundary conditions at 0. So it's essentially that formula. And but in this case, it has slightly different meaning. Here we have some source at the origin that produces spherical waves that decay as 1 over r. So, so we have a picture. We have a picture like this. And there are some waves that propagate to the right with decaying amplitude. So in the one-dimensional case, we would have this function simply moving to the right, and here we need to divide it by r, because uh, because in this case the energy per unit area should decay because the area of sphere increases with r, unlike in the 1D case. So, hmm?
I'm sorry, but maybe it's a bad question. Should we expect the height decrease with the r squared?
Uh, no, because it's a difference between potential and force. It's the same uh, for a stationary case. Because if you make this function simply constant, in a sense, our equation becomes time independent, and it is simply a Laplace equation. It is a 3D Laplace equation, and its solution should decay as 1 over r, because it's a gravitational or electrostatic potential. And if you want to compute the force, we need to differentiate it with r, uh, and Newton's gravity law in terms of forces becomes 1 over r squared. So was it? Wasn't this the origin of your question, or was it something different?
And so by this logic, the two-dimensional grid function should have like a logarithm.
At it's three-dimensional. Yes,
In the two-dimensional case, then we have a logarithm.
yes. But no, in a sense, here we will not get a logarithm. We will get logarithm for the time-independent case for the Laplace equation, but wave equation behaves differently, and it's qualitative difference. Yes. So, are there any other questions about this? So. Okay, let's now discuss such thing as reductions from this equation, uh, um, from from this equation and from its solution. Uh, so far we solved this equation, which is in 1 plus 3 dimensional space. So it was a complicated equation with f depending on t, x, y, and z. So one possible option is to say that letters f depend only on uh, mm, x, y, and z. F equals f of x, y, and z. So in this case, we can simply take this formula from the Green function. Mm. And so either take formula for the Green function and integrate it in time, or take this formula of a solution and say that f is t independent. and see that u of r equals to integral of d3r prime f of r prime over 4 pi absolute value of r minus r prime. So it's kind of one way to obtain this. Another way to obtain this is to integrate our gain function. Gain function of minus Laplacian equals to integral from minus infinity to plus infinity dt gain function of wave. Maybe dt squared minus Laplacian of t r. And if you integrate this expression in time, then it of course gives 1 from this delta function. So it will be 1 over 4 pi, 1 over 4 pi absolute value of r. And we already know this result from, for example, from reduction from the heat equation. So gain function of minus Laplacian. In 3 dimensions. So it's kind of consistent with what we know, but so it's fine. So it's kind of another way to get the same result. But now I propose to do a different thing, to perform a reduction in a space dimension. So I want this function to be functions of t, x, and y. Which means that we need to average everything over the last coordinate. So we can write that gain function for n equals to 2 of t, x, and y is a gain function for n equals to 3 integrated from minus infinity to plus infinity in z. Because if you take this function independent from the last coordinate, we can simply compute this integral from the very beginning and get a function that depends just on these 3 coordinates. So it's very similar to this formula, but now we integrate in z, not in t. So this gain function is integral from minus infinity to plus infinity dz. We set theta of t over 4 pi square root of x squared plus y squared plus z squared delta of t minus square root of x squared plus y squared plus z squared. So, let me write z in a different color so that we are able to track what we integrate. Okay, now there are we have this function of z, and we would like we first would like to ask if this function can vanish. In a sense, can this integral be non-zero? And there are two different situations. In so everything depends on whether square root of x squared plus y squared is greater than t or less than t. So if it is greater than t, maybe better try it like this: greater than t squared. Then what can we say about this integral? Yes, because the argument of delta function never vanishes. Because this term is always less. This square root is also is always greater than t. So have 0 in this case. And if x squared plus y squared is less than t squared, uh, mm, then we can find two solutions of this equation of the equation t equals to square root. Z should equal to plus minus square root of t squared minus x squared minus y squared. So we have just two contributions to this integral. So we first have Heaviside theta of t over 4 pi square root of x squared. Sorry. Maybe no. Maybe before writing formulas, let me first tell the general story about delta function that depends on some function of the argument. Maybe let's keep this, and there is this. f of z. Now, we would like to know what delta of f of z is. And to do this, we compute the integral of this delta function with some test function. So, and let this f of uh, z be some function with several zeros. F of z, z. So there are some z1, z2, zn. If we integrate delta of f of z with function phi of z minus infinity to plus infinity, we can restrict this integral to vicinities of the end, because delta function is zero in all other points when its argument is non-zero. So it is sum over from 1 to n, integral from the I minus epsilon to the I plus epsilon, delta of f of z, phi of z dz. Then, since we restrict to the small vicinities, we can move phi of z from the integral, writing that it is sum from I equals to 1 to n, integral from phi of the I, integral from the I minus epsilon to the I plus epsilon, delta of f of z and dz. So one step, next step is to say that since we are integrating this small domain, we can simply expand f of z as a Taylor series. So we have this integral, and now we want to change the coordinate. So we want to scale z by an absolute value of f prime. So you can write that it is integral from and oh, let me write this change of coordinates explicitly. We can write that z is zi plus x over absolute value of f prime of zi. So using this change of coordinate, you get phi of zi integral from minus epsilon prime to epsilon prime, it's somehow scaled, delta of x sine of f prime zi dx over absolute value f prime of zi. All right. So we got this derivative in the denominator. And now delta of x times sine is the same as delta of x. So this integral can be computed now, and we get simply sum from 1 to n phi of zi 1 over f prime of absolute value of prime of zi. So, and since this works for arbitrary test function phi, then what can we say about delta of f of z? So here we wrote that this is pairing between delta of f of z with phi of z. Can you write a function that can you write a generalized function that it does this for any test function phi? Uh-huh. Yes, thanks. Oh, z minus zi, because times 1 over absolute value of f prime of zi. So there's this simple formula. So it works also for z simply scaled by some factor. We just need to do the change of variables, but it works the same for arbitrary functions. So we can simply approximate f by linear function around each zero. And so there are there any questions about this formula? We've just checked that the left-hand side integrated with the arbitrary test function produces the same result on the right-hand side. It computes phi of the phi at all the zi's. Yeah. So, and I wrote this to apply in our case. So. So we see that here there is another step function which vanishes for for t squared less than x squared plus y squared. And we have integral in this, so we should treat this delta function as a delta of something of z. So uh, it, it is integral from minus infinity to plus infinity dz. We can divide here by 4 pi. And now we need to divide by derivative of this function. So this derivative is z over uh, square root of x squared plus y squared plus z squared inverse with z substituted to this value equals to plus square root of t squared minus x squared minus z squared. Maybe maybe better to write it for the full expression as if we already computed this integral. So let me remove this integral already and say that we have two contributions from these two zeros. So we have this expression with the substitute to plus root. And we have another contribution from another root. 1 over square root of x squared plus y squared minus z squared times plus z squared. But we see that actually these square roots cancel, and the final expression is and can erase this. The square root cancels, and we have 1 over absolute value of z, with z equals to plus square root of x squared minus x squared minus y squared. Plus actually the same expression, it's still 1 over absolute value of z with z equals to minus square root. So we have the same expression in both cases, and all this combines to heaviside theta of t, heaviside theta of t squared minus x squared minus y squared, divided by square root of 2 pi square root of t squared minus x squared minus y squared. So this is the two-dimensional green function, and the main point is that if you compare it with the 4D case, it is now non-zero for all values of t inside the right cone. So let's compare the two pictures to 2D. In 2D, we have a green function that is delta function concentrated on a line, but in the 2D case, we have so this is R and this is T, and here R T. Here we have 0 and 0, and here we have something. Here and here it is non-zero. We have some profile of this green function, if you wish. So in this case, delta green function of t for fixed r behaves like this. It is just or maybe delta function of r for fixed t. Maybe this is better. It's maybe no delta function of t for fixed r behaves like this, and in this case green function of t for fixed r behaves like this. So here we have two sharp fronts, forward and rear. And here we have just one. So which means that if our space was two-dimensional, we would not be able to talk to each other, because every sound would be accompanied by the infinite echo, which decays quite slowly. It decays like 1 over t, and most of human senses measure the intensity of sound or of light more or less algorithmically in some intervals. So this 1 over t decay would mean quite slow decay. So. And the situation is the same for all odd dimensions and all even dimensions. So in a sense, this one-dimensional case was an exception. This constant value of the green function counts more or less like zero, because it is like a minus first derivative of delta function, and in higher cases we will have first, second derivative of the gain function. In this series of dimensions, and in this series of dimensions, we will have a gain function without sharp rear front. So this integrals can be computed, but it's technically a bit complicated, but doable. Yeah. But it's so it's not the most complicated behavior of PDEs. The most complicated case is when we also add the mass term, if you turn it into a Klein-Gordon equation. Uh, but like this. In this case, those GAN functions are described by special functions, Bessel functions. They have this singularities, but we will not study that case because it's too complicated and not very useful. But if we restrict to equations without this term, then this is the most complicated gain function, which shows its dependence on dimensionality. And we already know all other gain functions for the heat equation and for Laplace equation. They have more or less a universal formula for different dimensions. So, yeah, do you have any questions about this? Okay, and all other computations, I think, will be less technical. So we'll and not need to compute all these integrals. But here I think it was worth to do this to see these different behaviors because it's conceptually interesting. Okay, thanks for your attention.